Hello, everyone. Welcome to today's presentation. I'm excited to introduce our topic, polynomials. This will be a fascinating journey into understanding some fundamental concepts in mathematics. We'll cover what polynomials are, explore their properties, and see how they're used in various applications. But for now, let's keep it short and get started. I look forward to sharing this with you. Welcome to Slide 2, where we explore the contents of our presentation. We'll start with the introduction to polynomial concepts, then move on to important terms that form the foundation of our study. Next, we'll look into the different types of terms involved in algebraic expressions, followed by the various ways to classify algebraic expressions based on their terms. We'll also cover the different types of polynomials categorized by their degree, which is crucial for understanding their behavior. Then, we'll see some practical examples to solidify these ideas. Moving forward, we'll discuss key theorems like the factor theorem and the remainder theorem, which are instrumental in factorization and division of polynomials. Additionally, we'll examine the standard form of a polynomial, which helps us analyze and manipulate these expressions more easily. Lastly, we'll touch on algebraic identities that frequently appear in algebraic manipulations. And of course, we'll conclude with a thank you, acknowledging your attention and participation. Throughout this presentation, our goal is to build a clear understanding of polynomials, their properties, and their applications, connecting each topic to the bigger picture of algebra. Let's talk about algebraic expressions. In mathematics, an algebraic expression is essentially a combination of constants, variables, and the basic operations like addition, subtraction, multiplication, division, and exponentiation. The key point here is that the exponents are rational numbers, which means they can be fractions, not just whole numbers. For example, consider the expression 2x cubed minus 4x squared plus 6x minus 3. This is a polynomial in one variable because all the exponents of x are whole numbers, specifically non-negative integers. Similarly, 8p to the 7th plus 4p to the 5th plus 11p cubed minus 9p is also a polynomial, but in the variable p. Now, here's an interesting point. Look at the third example. 4 plus 7x to the power of 4 over 5 plus 9x to the power of 5. This is still an algebraic expression, but it's not a polynomial because it contains a term with x to the power of 4 over 5, and that fractional exponent means it's not a polynomial term. So the main idea is that polynomials have exponents that are whole numbers, while algebraic expressions can include fractional exponents, making a difference in their classification. This understanding is essential as we move forward in exploring more about algebra and its applications. Now, let's explore some important terms related to polynomials. First up, polynomials are algebraic expressions where the variable involved only has non-negative integer powers. For example, you might see something like 3x2 plus 4y. Notice how the powers of the variables are whole numbers, which is key to a polynomial. Next, we have constants. These are symbols that represent fixed numerical values. In our earlier example, 3 and 4 are constants because they don't change. They stay the same regardless of the variables. Moving on to variables, these are symbols that can be assigned different numerical values. For instance, in 3x2 plus 4y, both x and y are variables because their values can vary depending on the situation. Now let's talk about the degree of a polynomial. This is simply the highest power of any variable present in the expression. For example, in 5x2 plus 3, the highest power is 2, so the degree of this polynomial is 2. The degree gives us a sense of the polynomial's complexity and behavior. We also have constant polynomials, which contain only a single term that is a constant. Think of something like 3, minus 5, or 7, 8. These are called constant polynomials, and interestingly, their degree is 0 because they don't have any variables. Finally, there's the zero polynomial, which consists of just one term, the zero itself. Its degree isn't defined because there's no highest power to consider. These terms are fundamental because they help us understand and classify different types of polynomials, which ties back into our overall theme of exploring algebraic expressions and their properties. Let's talk about the different types of terms you'll encounter. First, we have like terms. These are terms that share the same variable and the same exponent or power on that variable. For example, 3x minus 7 2x and 8 9x are all like terms because they all involve the variable raised to the first power. Recognizing like terms is important because it helps us simplify expressions more easily. Now, on the other hand, we have unlike terms. These are terms that do not have the same variable or the same power of the variable. For instance, 7a, 8b, and 19.3c are unlike terms. You can't combine them directly because they involve different variables. Understanding the difference between like and unlike terms is fundamental when we're simplifying algebraic expressions. It allows us to combine only those terms that are truly similar, leading to a cleaner, more manageable expression. This concept ties into the overall theme of algebraic simplification and manipulation, helping us work more efficiently with equations. Now, let's explore the different types of algebraic expressions based on the number of terms they contain. First, we have the monomial. A monomial is simply an algebraic expression with only one term, like 3x2 or 4y. It's the simplest form of an expression, and understanding it helps us build a foundation for more complex types. Next, we move to binomials. These are expressions with exactly two terms, such as 3x2 minus 8y2 or x2 minus 4. Recognizing binomials is important because they often appear in factorizations and algebraic identities. Then there are trinomials, which include three terms. An example would be z2 plus 4z minus 9. Trinomials are particularly common in quadratic equations and factoring exercises, making them a key concept to understand. Finally, we have polynomials, which are algebraic expressions with many terms, more than 3. An example would be 3x3 plus 4x2 minus 2x minus 7. Polynomials are fundamental in algebra because they appear everywhere, from simple equations to complex functions. Connecting all these types helps us see how algebraic expressions are categorized and how each plays a role in solving different kinds of problems as we progress in our understanding of algebra. Now, let's explore the different types of polynomials based on their degree. First up is the linear polynomial. A polynomial with degree 1 is called a linear polynomial. Think of simple expressions like 3x or 4y. These are perfect examples. They're called linear because their graphs are straight lines, which makes sense given their degree. Next, we have the quadratic polynomial, which is of degree 2. For example, something like x2 plus 5y2 minus 9. Quadratic polynomials are quite important because they produce parabolic shapes when graphed. They appear often in areas like physics, engineering, and even economics. Moving on to cubic polynomials, these are of degree 3. An example would be x3 minus x2 plus 5x minus 7. Cubic functions are interesting because they can have turning points and inflection points, giving them more complex shapes. They often model real-world phenomena that involve changing rates. Finally, we come to the biquadratic polynomial, which is of degree 4. An example here would be 3x4 minus x3 plus x2 plus 5x minus 7. These are a bit more complex, but are useful in specific applications like optimization problems and advanced modeling. So, understanding these different types helps us classify polynomials and predict their behaviors based on their degrees, which is a key part of mastering algebra and calculus. Now, let's look at some examples to understand how polynomials are classified. First, consider the polynomial 5. Since it has only a constant term, its degree is 0, which makes it a constant polynomial. These are the simplest type of polynomials. Next, take 2x minus 4. This has a degree of 1, which classifies it as a linear polynomial. You can think of it as a straight line when graphed. Moving on, look at 3x squared plus. This polynomial has a degree of 2, making it quadratic. Quadratic polynomials often produce parabolic shapes when graphed. Finally, consider x cubed minus 4x squared plus 1. Its degree is 3, which makes it a cubic polynomial. Cubic functions can have more complex shapes, with the potential for multiple turning points. These examples help illustrate the classification by degree and the number of terms, reinforcing how understanding these categories is fundamental to mastering polynomial functions. Now, let's talk about how to convert a polynomial into its standard form. The key idea here is to arrange the terms so that they are ordered from the highest degree to the lowest degree. This makes the polynomial easier to work with and analyze. To do this, we start by identifying the degree of each term, which is the exponent on the variable. Then, we rearrange all the terms so that the term with the highest degree comes first, followed by the next highest, and so on. It's important to combine like terms, those that have the same variable raised to the same power, to simplify the polynomial. This process not only makes the polynomial easier to read, but it also helps when performing operations like addition, subtraction, or evaluating the polynomial at specific values. Overall, converting to standard form is a fundamental step that streamlines working with polynomials and connects to the broader theme of understanding their structure and behavior. Let's take a closer look at the remainder theorem. Imagine we have a polynomial function f(x), where the degree of f(x) is greater than 1, and we pick any real number now if we divide f(x) by the binomial x. What do you think the remainder will be? The theorem states that the remainder in this division is actually just f(a's). Now, to understand why this is true, let's consider the division process. Suppose the division yields a quotient g, x, and a remainder rx. Since we're dividing by a linear binomial, the degree of the remainder rx must be less than the degree of x, which is 1. That means the degree of rx is less than 1, so rx must be a constant. Let's call it r. From the division, we can write the original polynomial as f(x) equals x times g. X plus r. If we substitute x equals into this equation, the term x becomes 0, leaving us with f(a) equals r. So, the remainder when dividing by x is exactly f(a). This is a powerful result because it connects the value of the polynomial at a point directly to the remainder of this division. It's a key concept that helps us evaluate polynomials more efficiently and connects algebraic division with function evaluation, which is fundamental to understanding polynomial behavior. Let's take a closer look at the factor theorem. Imagine we have a polynomial function f(x) of degree n, where is greater than 1. Now, if we find that f(a) equals 0 for some real number, this is a significant point. It tells us that the value of the polynomial at x equals is 0. What does this imply? Well, it means that x(a) is a factor of f(x). In other words, the polynomial can be broken down into x multiplied by some other polynomial g, x. To understand why, let's consider the division process. When we divide f(x) by x, the quotient is g, x. According to the remainder theorem, the remainder of this division is exactly f(a). Since we know f(a) equals 0, the remainder must be 0 as well. So we can write f(x) as x times g, x plus 0, which simplifies to f(x) equals x times g, x. This confirms that x is indeed a factor of f(x). This theorem is powerful because it links the roots of the polynomial directly to its factors, making factorization and solving equations much more straightforward. It's a fundamental concept that connects the value of the polynomial at a specific point to its algebraic structure, which is essential for understanding polynomial behavior overall. Let's dive into some algebraic identities that are fundamental in simplifying complex expressions and solving equations. First, we have the square of a binomial, a plus b2. This expands to a 2 plus 2ob plus b2. Similarly, for a b2, the expansion is a 2 minus 2ob plus b2. Next, there's a very useful difference of squares. A 2 minus b2 equals a b, a plus b. This allows us to factor quadratic expressions quickly. Moving on, when we multiply two binomials like x plus a, x plus b, the expansion results in x2 plus the sum of a and b times x, plus the product of A and B. Now consider the square of a trinomial, A plus B plus C2. When expanded, it becomes the sum of the squares of a B and C plus twice the pairwise products, 2ab, 2bc, and 2ca. Similarly, the cube of a binomial, A plus B3, expands to a 3 plus B3 plus 3 times ob times A plus B. For the difference of cubes, a B3, the expansion is a 3 minus B3 minus 3 times ob times a B. There are also formulas for the sum and difference of cubes. A 3 plus B3 equals A plus B times a 2 minus ob plus B2, while a 3 minus B3 equals a B times a 2 plus ob plus B2. Finally, there's a more advanced identity involving 3 variables. A 3 plus B3 plus C3 minus 3 ABC equals A plus B plus C times a 2 plus B2 plus C2 minus ob minus BC minus ca. An interesting special case occurs when A plus B plus C equals 0, in which case the sum of their cubes simplifies beautifully to 3ABC. Understanding these identities is crucial because they serve as building blocks for algebraic manipulations, simplifying expressions, and solving equations efficiently. They connect deeply with the overall theme of mastering algebra, helping us see patterns and structure within complex expressions.